Hello everyone and welcome to Sleight of Arm Demystifying Intel Houdini. My name is Brian and I'll be discussing Intel's Houdini binary translator, so what it is, where it's used, how it works, security concerns, and recommendations. Before that, a quick little bit about myself. That's me. I studied electrical engineering at the Cooper Union and I'm currently a security consultant with the NCC group, where lately I've been performing a lot of Android pen tests and sometimes even Android malware analysis. Besides that, I like to build random bits of hardware, as well as reverse engineering low-level stuff that other people build, both hardware and software. And with that, let's get started right on to Android. So, Android is one of the largest operating systems, powering about 70% of the mobile devices in the world. And most of you know that you can write applications for Android using Java and now Kotlin, as well as C and C++ for native applications using the native development kit. Um, Android was originally designed and built for ARM devices, but Google later added support for x86. And just to note, there has been unofficial support for x86 before that as well, such as the Android x86 project. Um, Continuing on this background on Android, um, so there have been several devices on x86 running Android, but now there are mainly two, and those are x86 Chromebooks and x86 hosts running commercial Android emulators. However, apps still generally lack support for x86, and that's because ARM was and is the primary hardware platform for Android. In fact, if you have native components in your app, the Play Store only requires the ARM builds. Um, and due to this, many native applications don't end up containing x86 binaries, only ARM. So, the question is, how can these x86 Android devices run those apps that only contain ARM binaries? And this is where I'd like to introduce you to Houdini, the topic of this talk. Um, Houdini is Intel's proprietary binary translator that allows x86 devices to run ARM binaries. It was co-created with Google as it was designed to be run with Android Native Bridge, which we'll talk about in a second. It's a mysterious black box. We don't know how it works, and there doesn't seem to be any real documentation on it. Some vendors may be trying to hide that they're using it. We may or may not talk about that. And there are three variants, as you see. Um, and so, Houdini, where is it used? It's used in physical hardware, such as the x86 based phones, which we don't see much anymore, and x86 Chromebooks, which is actually how we were able to get the binaries. It's also used in some commercial emulators, and there's also the Android x86 project, which can be run on a real device or in an emulator. So, how does it work? Um, it's basically an interpreter for ARM instructions. There's a loop reading the ARM opcodes and produces the corresponding behavior in x86. Do want to point out that it does not JIT. It doesn't translate and output x86 instructions. It just reads the ARM code and then emulates the behavior. There are two main components, Houdini and libhoudini. The first of which, just called Houdini, runs ARM executable. It runs ARM executables, yeah, both statically and dynamically linked. When running dynamically linked executables, it uses its own set of precompiled libraries for ARM Android, in addition to the x86 libraries needed by Houdini itself. Um, we can see below that the machine I'm running on is an x86 machine. That's actually from the Chromebook. You can see i686 x86 machine, and the binary we're trying to run is a 32-bit ARM. But when I try to run it, it just works fine. Hello static, prints out hello world. Classic. Um, some of you may have noticed that I've just executed the binary directly without invoking Houdini. So you might be asking, where does Houdini come from? And this is actually a feature of the Linux kernel called bin format misc. And if you aren't familiar with it, here's a really quick explanation. Miscellaneous binary format is a Linux kernel feature that lets you basically register interpreters for custom binary formats. Kind of similar to how a shebang works in Bash or Python programs, but on the kernel side, kind of. And in this case, our custom binary format is on ARM ELF. So we see that there are entries registered for static and dynamic ARM ELF binaries, and those are the corresponding magic bytes. And the interpreter is set to system bin Houdini. So in other words, when I run /hello, it becomes, it compares the magic bytes, and if it matches, it becomes system bin Houdini /hello. So that's how the executable Houdini is used. So let's take a look at the second component. libhoudini.so, which you could probably guess by the name, is a shared object. It is a shared object for x86, and it's used to load other shared objects built for ARM. So this is the part where it's designed to be used with Android Native Bridge. So let's talk about that. Android Native Bridge is what allows this binary translation to work on the Android side. It is part of the Android runtime and is the main interface between Android and libhoudini. So the Android Native Bridge is the interface, and you could think of libhoudini as the implementation of that interface on the binary translation side. So given that, I want to point out that while it might have been designed with specifically ARM and libhoudini in mind, the interface that Native Bridge provides can be used to implement other processor architectures. For example, MIPS on ARM. I just thought that was kind of cool. But delving deeper into Native Bridge, I mentioned it's part of the Android runtime, so it is initialized on boot. And during initialization, it checks that system property, RO-Dalvik VM Native Bridge. If it's 0, Native Bridge is disabled. But in our case, it's set to libhoudini, which points to the library file that implements Native Bridge. And we'll look for that in the library paths. If you actually take a look at Android x86 project, it seems like they use their own implementation of Native Bridge, called libmb.so, but when you take a closer look, it's actually a thin wrapper around libhoudini. It just calls libhoudini functions. And Native Bridge defines interface with two callbacks, Native Bridge runtime callbacks and Native Bridge callbacks. And before I get into that, I really have to quickly explain Java native interfaces because they use JNI really heavily. So quickly, Java native interface is the foreign function interface that enables our JVM code, the Java code, to interact with the native code, and vice versa. So actually, this JNI stuff is part of Java and not specific to Android. So it would be much easier to find information on it. And when the Java JVM calls a JNI compatible native code, it provides a pointer to a struct JNIM, and this JNIM basically is basically a bag of function pointers that can be used to perform low-level JVM reflection. And it's shown on the right, the JNIM struct. And some of the examples shown here are, allocating new objects, calling methods, getting some object fields, and such. So yeah, a pointer to this struct will be passed to our native code as a first argument, so that our native code, if they wanted to interact with the Java world or call methods or get objects, it could do it using that way. So back to the Native Bridge callback interfaces. The first one was called Native Bridge Runtime Callbacks, and it's passed from our Native Bridge on the Android side to libhoudini, so that libhoudini can call other native functions in Native Bridge /Android. And it's just simple. It's three things: get method shorty, get native method count, get native methods. And that is, I think, from the Android source. The second, more interesting struct is called the Native Bridge Callbacks, and it is basically the opposite. It provides a way for a native bridge on our Android side to call functions in libhoudini. And there's like a handful of function pointers in there, but I think the most interesting are Initialize, load library, which is similar to dlopen, and get trampoline, which works similarly to a dlsim, which I'll get to in a bit. And this struct is actually provided by libhoudini via the exported symbol native bridge ITF, and we can see that by doing object dump. And when you look at it in Ghidra, you see the actual bytes, the function pointers. Uh, right, right. So I've kind of just thrown a lot of pieces at you, and I'm going to try my best to explain how all of this comes together. Here we go. So this is on a regular ARM device trying to run an application that contains native code, ARM native code. This is a normal situation, your phone. Um, you launch your app, and your app um, has code, something like system.load library or load. So that triggers the Android runtime to dlopen our native native library, libnative.so, and then when our Java code wants to call it, it first does a dlsim, which returns a function pointer to our native code, and then jumps to it, and the Android runtime passes in the pointer to jninv when it does the actual function call. Now this gets a lot more complicated with native bridge enabled and with libhoudini on x86. So this is what it starts off with. So remember, native bridge is initialized on boot. So on boot, before anything happens, if it sees that native bridge is enabled, it opens the implementation library. In our case, libhoudini.so. And note that the top two boxes are x86, and the bottom one is our native ARM code that we want to run on our x86 machine. So yeah, our Android runtime on initialization calls dlopen and loads our libhoudini, and then it does a dlsim for that native bridge callbacks struct, and calls Initialize, which isn't shown in the diagram. Alright, and then the Android finishes booting up, and then you launch your app, and the application once again does something like system.load library. This time though, because native bridge is enabled, and it's x86, we can't just do dlopen on our ARM native library. And native bridge knows to um, call libhoudini's load library function from that native bridge callback struct. And the load library function acts similar to dlopen, and that it will load the actual native library in memory, and then give you a handle. Um, right. We can't call dlopen because it won't let you load a library of a different architecture. Like it will give you an error or something like architecture mismatch or something like that. So when our application code now wants to actually jump to the code, native code, we can't do a dlsim for the same reason. It would give us architecture mismatch. And also, if it actually gave us the function pointer into our native code, um, the function will contain a bunch of ARM instructions, which our x86 processors cannot understand. So what getTrampoline does is it actually gives a function pointer to a little stub inside of our interpreter, so that when we call that interpreter, the interpreter starts running our native code. That part is, yeah. But we have one last part that I have to explain, which is the jninv structure. Not only do we have to so for the same reason we can't just get the function pointer to our ARM native code, we can't pass our jninv, which is full of x86 functions, into our native code, our ARM code. So basically we can't do that. Um, so what libhoudini does is it actually remembers where the jninv that was passed in, where it was, and then it creates its own fake jninv structure filled with ARM function pointers, and it uses that to pass to our ARM native code. Um, so yeah, so actually when you try to call use any of the JNI functions from that struct, the actual function will just have um, trap instruct. It will actually have syscall instructions, which will be interpreted by our interpreter inside of libhoudini, and depending on the syscall number, libhoudini knows which x86 JNI function to call. Uh, yeah, this part is probably one of the most confusing parts to explain and understand. So continuing on, let's delve deeper into the libhoudini of different components inside of libhoudini. So first up is memory. It is a dual architecture userland, so um, it loads both ARM and x86 binaries. I'm going to combine the second and third bullet point, shared virtual address space and real-world view of memory. That just basically means they share an address space. There's no like magic translation between like ARM memory address and x86 memory address. They're just all in the same memory. And the ARM, yeah, has its own separate allocation for stack. And just to show you some examples, this is a snippet from one of the processes memory map of an application with libhoudini and native bridge enabled. We could see our native library loaded in here as well as our libhoudini on the bottom. These are the ARM libraries mapped in. You can tell by /vendor/lib/arm/nb native bridge. Yeah. Um, you can see there's both ARM and x86 versions of libc loaded in, and there are some anonymous pages. Anonymous pages used internally by libhoudini. One or more of these will be the ARM stack. So moving on, the actual execution loop. So I mentioned earlier, it's basically a switch statement inside a while loop. This screenshot shows the portion where the interpreter reads the ARM instruction and jumps to the proper instruction handler depending on which instruction it is. You can see my comments on the right, but I will have a C equivalent code on the next slide. So this is the fetch decode dispatch. So that code from before, so it reads the next instruction from it gets the current program counter from the processor state data structure, which we'll discuss later. So from the processor state data structure, we get the current program counter, and it loads the next instruction into this variable. The condition code, which I think in ARM is the 8 most significant bits of the instruction for ARM. So those 8 bits are checked to see whether the instruction should be executed or not. And once it determines that the current instruction should run, it combines the bits 20 to 27 and 4 to 7 to form an entry index into this instruction handle table shown on the right, which is filled with function pointers to different instruction handlers. So, for example, for the instruction move R0 R1, there's a calculation, and we get an entry index of 0x181. To get the actual byte offset, each entry is 4 bytes long, so you multiply by 4, you get 0x684, and when we add it to the instruction table base, we get 0x4bc044, and that looks like that. You can see on the left the address and the function pointer, instruction move 1. I just named it that. And on the right side, you can see the not entirely correct code. This is assembly, decompiled code, I guess. Decompile, yeah. Yeah, we can see on the right side that we are seeing some registers being moved around and shifted. But the important thing is that it takes in every instruction handler takes in 2 parameters. The first one is the instruction itself, so the handler function could pull out all the operands, stuff like that. And the second argument is the pointer to the current processor state. So the processor state struct keeps track of the ARM processor state. Fairly simple. Mainly there is the registers, which contain stuff such as the program counter and the stack pointer and the general purpose registers. And there's another field in the processor state that tells you whether it is currently in thumb mode or not. There's many other fields in there which I couldn't really figure out what they're all being used for. But once you know where the struct is, you could kind of read and or write from it from both ARM and x86 side because they have the same uh, memory view and they're in the same memory address space. And this there was an issue with this where every time across boots and every time you relaunch an app or anything, it would be at a hard-coded fixed address at that specific address. They have fixed it now, um, but yeah, that is a problem because you could just write to it and change the execution state of the ARM emulation. So next thing we took a look at was the syscalls. How do they handle syscalls? They're handled pretty much the same way, going through the instruction handler table, except that in the actual syscall handler function, it doesn't actually make any syscalls. It just sets the syscall number in the processor state um, from here, the unsigned in SVC number. It just sets that number and then returns, and then all the syscalls are handled further down the execution loop. And there is a giant function that performs different syscalls based on that value. Most of them are just simple wrappers or pass-throughs with some conversions. For example, the open syscall, and that's not really architecture dependent. So you might have to move around the registers to get in the different format, but it's just a wrapper to call the actual open syscall. But some other syscalls do more complicated things. Specifically, we were interested in the clone syscall. So we want to see how fork/clone was handled. Fork was included because nowadays, when you call fork, it actually calls a libc fork, which in turn performs a clone syscall. Clone stood out. It was interesting because one of its required arguments is a child stack pointer. Um, and that child stack pointer, you allocate some address, and then you push a return address to the top of that stack, and then you pass the pointer to that stack to clone, and that new child stack will become the stack of the child when clone clones the process. Um, and this was interesting because from ARM we were passing out child stack with the return address pointing to our ARM code. So we were wondering how Houdini handles that. Turns out Houdini re-implements it. It creates a new RWX page and passes that instead. And then it handles the parent and the child logic. And then, yeah, um, it got a little fuzzy, but it just re-implements the whole thing. Um, yeah, right. So now that we have some ideas on how it works internally, let's try to get to some of the fun stuff. So I was thinking like if you were an app or if you're um, well, are there ways you can know whether you're running on a real device or a device with lib Houdini? So we're talking about detection. We came up with a couple ways. One of them is we build an ARM native app, right? And we could check the host architecture, either via Java's OS Arch system property or via reading the proc CPU info. Because if you built an ARM native application, but and it's running, but if its actual architecture is x86, there's a high chance you're running on the lib Houdini. But turns out you actually can't use this method because Houdini hides those. When you do system.getProperty OS Arch, it will say armv7l. And when you try to read cat proc CPU info, it will say ARM as well. Although you might be able to tell because those two answers came from the same machine. One says ARMv7L, the other one says ARMv8, AR64, and hardware says placeholder, serial number is 0. Yeah. So next method was checking the memory map. via reading proc self maps or seeing if both the ARM and x86 shared libraries are loaded in. This is a okay method, but we think the best ways would be the ones that are hard to detect themselves, like quiet detection. So best implementation is one that issues no otherwise discernible syscalls, and the method we came up with was using the JNIM magic pointer detection. Um, right. So if you're on a real device, when we get the JNIM function pointer, those function pointers would contain real ARM instructions. But on their libhoudini, those function pointers would be just syscall instructions. And that may be one of the ways you could tell whether you're running inside libhoudini or not. The second thing we could talk about is possibly escaping to x86. Now, your application doesn't know, um, or your native application thinks it's running in ARM. Uh, Now, whether you're running on a real ARM device or x86 device with ARM with libhoudini, you could tell using the detection method. But once we detect that we're running inside of Houdini, can we escape to x86? Of course, there's we're running our code, so we could always just call like mprotect and overwrite code to memory. Um, but again, this isn't very subtle, and also like any decent analysis tool would probably flag this immediately. Um, so the we could also figure out trying to find where the x86 stack is, so we could clobber the stack with raw payloads and have it jump to somewhere. Um, but that's also a lot more annoying, and I'm just gonna say it. There's just a bunch of RWX pages laying around, which you could just write code to and jump to. You could write x86 instruction to them, and then jump to it. Well, you wouldn't be able to jump to it from the ARM side. Um, so just to point out what some of these pages are used for, um, that's that's where the JNIM structure lives. That's where the ARM stack is. You know, but yeah, there's RWX pages on the x86 side, which there shouldn't be. Um, so what about getting like Sidechannel code execution on ARM side? Um, Turns out the NX bit is ignored entirely by Houdini. Um, Not that this behavior is correct, but if you think about it, it kind of makes sense. Houdini is an interpreter for ARM instruction, and the ARM opcodes are data. If Houdini could read it, it will run it. Um, so this means you could just write code anywhere and jump to it. Uh, don't think I need to say much more about it. And to show you, I have this little program. Uh, I just allocate some memory on the buffer, code 512, initialize it with 0. I write two things in there. They're ARM instructions for adding 1 and then returning. And I cast to a function and I call them. Normally, that on a real hardware would cause a seg fault, jumping to stack. But here we see that it just ran fine. This is also on the Chromebook. Um, Actually, the first iteration of this code, I actually had the uh, int code buffer outside of the main, so it was in like not on the stack, and that also ran fine. Um, Demos, I'm not sure if I'll have time for demos. Um, but let's talk about if you're a malware, you don't wanna you wanna avoid detection and analysis. And to do that, one way would be to just hide yourself when you think you're under analysis. And we know that applications are often run in sandbox environments for analysis. This is mainly done in one of three ways. The first of which is running them on actual devices, which this would give the most realistic behaviors, but it's also hard to do on a large scale and also often very hard to instrument. The next option is fully virtualized environments like QEMU, but these also have somewhat of a performance overhead since they will be emulating the entire hardware. Um, and that brings us to our third option, Android emulators, which runs x86 Android but uses technology like Houdini to run ARM application. This has the least overhead as it would only emulate parts of the applications. So, um, a malware could use one of the detection methods that we mentioned earlier to figure out whether it's running with or without Houdini. Then it might be possible for the malware to act benevolently when it thinks it's under analysis, and then show malicious behaviors when libhoudini is not present. Right. What about the other way around? We could also prefer malicious actions only when Houdini is present, abusing the knowledge of its internals to further obfuscate itself. Um, right. Let's say we could overwrite the processor state to do some things that the analysis tool doesn't know how to understand. Um, well, given all that malware talk, our recommendations to vendors and platforms, um, and how to not write an emulator. So, firstly, we should not map things to deterministic addresses, especially important data structures like the processor state struct, which has been fixed by Intel. Um, the second recommendation is drop the unnecessary RWX pages. If you really need them, perform fine-grained page condition control. And this kind of leads to the next one. Um, we could implement, so on the Houdini side, Houdini ignored the NX bit. Don't do that would be my security advice. Uh, do not ignore the NX bit, which tells you whether you can execute or not execute in this memory. Um, so we understand checking page permission every instruction would incur significant overhead. So instead, we just keep track of the mappings and permissions in process, kind of like page tables. Um, and only perform checks if an instruction is, um, going across the page boundary or jumping somewhere, which would reduce the performance overhead. Um, but actually, because you're basically building a userline page table, use virtualization, is our recommendation, which would solve, well, yeah, use virtualization and use ASLR to protect sensitive data structures. Um, so speaking of the userline page table, this is some of the ways we think can be done. Trust only the text sections on load and check um, the page mappings uh, every time a new page has been added. Or we could just, is, you know, libhoudini has hooks for all the syscalls, so instrument those memory mapping related syscalls to track page permissions. Um, and actually, the ideal solution combines 2 and 3 with the checking the proc self maps for as a catch-all, and this would actually enable dynamic uh, loading via DLOpen, and it will support legitimate JITing, and making sure to remove the pages when JIT is finished. Um, right, and of course, this data structure should be heavily protected. Um, Writable only when being updated surrounded by guard pages and not accessible through ARM, etc. And for people doing analysis on applications, you should also run these apps through libhoudini and dynamic analysis instead of just trying it on random hardware or on a VM or like a full camera environment. You should also do static analysis to look for access to weird Houdini read-write execute pages or any attempt to execute from non-executable pages because Houdini allowed this. And also because of our JNI-env detection method, uh, you should also look for anything scanning the JNI-env function pointers. So this brings us to our conclusion. Houdini introduces a number of security weaknesses into processes using it. They weaken both the security of the ARM and the x86 code. And I think that the fact that this Houdini is not well documented publicly nor easily accessible has something to do with these issues which could have been found earlier through research. And this is our disclosure timeline. We sent the first set of findings to Intel. They promptly acknowledged it and fixed it, provided us an update. And for the seconds, we also provided them a second set of findings, and they were happy to let us know that the new version is now available. Um, if you're an OEM, you can find patches, new versions of these, I guess. And big special thanks to Jeff for mentoring and helping develop the methodology, Jennifer being all the support and research and like amazing feedbacks, and Effie for basically bootstrapping this research. And with that, thanks everyone for joining, and I think we are at Q&A.